Okay. So, questions from you guys. You guys should have tried this homework 5 last night.
You do number 3.
3? Sure. All right. I start off by noticing that there should be 4 solutions because the degree of that polynomial is 4. I know that my possible rational solutions are going to be the factors of 24 divided by the factors of 1. So the factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. And then to figure out which one of those factors I want to use, I'm going to have to then look at the graph of this polynomial. So I'm going to go and type that into my calculator exactly as it's written. So I have x to the 4th minus 4x to the 3rd minus 7x squared plus 22x, 22x plus 24. And then I'm going to set my window. So if I look at my RRT list, the smallest number on that list is negative 24. And the biggest number is positive 24. So I'll set the x min and x max to match that. And then I'll hit graph. So it looks like all the stuff that I'm interested in is over here. So I can get a little bit better picture by cutting out this section and this section. I don't know what that negative 5 to positive 5 seems like it would be enough. So if I look here, we have negative 3. Negative 1, positive 3, and positive 4 are my x-intercepts. You agree with that, Leo? That's basically what it looks like in our picture here, right?
Negative 2.
Oh, thank you. Yep. Negative 2, negative 1, positive 3, and positive 4. Yeah. Okay. So far, so good?
Yep.
Okay. Let's pick one of these then, since they all match, right? Negative 2 is here, negative 1 is there, positive 3 is there, and positive 4 is there. Any of these would be a good starting spot. So it doesn't matter which one we choose here to start with. So let's just pick maybe the negative 2 because it was the first thing on our list to start our synthetic division. And then I'm just going to take the numbers from my polynomial, the coefficients from my polynomial, and start my synthetic division. So bring the 1 down. Negative 2 times negative 1 is times positive 1 is negative 2, and I add down that's negative 6. Negative 2 times negative 6 is positive 12. I add down that's 5. Negative 2 times 5 is negative 10. I add down that's 12. Negative 2 times I add down that's 0. So what I can say here then is that this tells me that I factored to x plus 2 times x cubed minus 6x squared plus 5x plus 12. And you could try to factor that 4-term polynomial there at the end, but you're going to find that grouping doesn't work on it. So what we'd have to do is we'll have to do another synthetic division. So the numbers I can choose from, we've already used -2. So I could use -1, +3, or +4. I'm going to choose -1 just because it's the next one on my list. And I'll continue on doing my synthetic division. And once again, that works. So what this tells me is still the x plus 2, but now that other polynomial factors to x plus 1 times x squared minus 7x plus 12. And at this point, the x squared minus 7x plus 12, you should notice is something that's factorable, so you could factor that. If you had not noticed that, though, you could continue doing your synthetic because we still have numbers left on our list. So I could continue going and say take the 3 and do the synthetic division again. And that'll give me the final answer, or you could have factored that to get the final answer, depending on which one you feel more comfortable with. Since we still had more numbers to use the synthetic division with, we could still keep going, or you could have stopped and factored at that point. Either would have been okay. Is that okay, Leo?
Yeah, I just did the synthetic division part wrong.
Yep. So again, the fact that you should know that you should be getting 0 remainders should be a good cue that if that doesn't happen, you probably just made like an arithmetic mistake during the synthetic division.
Yeah, every one I would times -2 by the 1 first, then put it at the bottom, not just bring the 1 down.
Oh, yep, that would do it. Yeah. Okay. Well, that's an easy fix, though,
Yeah,
right?
I know.
Yep. Good. Who else wants to talk about this assignment from last night? Again, I acknowledge it's not a trivially easy process, right? There's kind of a lot of stuff going on here. So I'm happy to do more. If I'm going too fast or I'm doing something you don't understand, feel free to interrupt and ask me to clarify or rehash or re-explain. I'm happy to do that kind of thing. I know this is a lot all at once to be, a lot of ideas kind of coming together. So if I need to slow down or if I need to re-explain something or you're just not sure, please stop me and interrupt. Or if there's more things that you want to talk about or whatever, like it's important that you understand what's going on. And I want to do as good a job as possible, but I don't live in your head, So if something's not going well for you, please speak up and talk to me. God bless you.
Thank you.
You're welcome. Anybody else here?
Is that cool?
Yes.
Can you please do number 5?
5? Sure.
5, 6.
Okay. So 5, again, we'll start out by observing that we should have 4. And if we look at our rational roots theorem, we're going to have the factors of 30 divided by the factors of 2. So my factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. So that's over 1. And then I also have each of these over 2. Because we have our leading coefficient is 2, so the factors of 2 are 1, which is what I have above. and then 2, which is what I'm writing now. If we notice, though, on that second line, I've written some duplicates, right? 2 over 2 is the same as 1 that I already have up there. Similarly, 6 over 2 is the same as 3, which I've already written down. 10 over 2 is the same as 5, which I've already written down. And 30 over 2 is the same as 15, which I've already written down. So I'm just going to cross those out because I know that I don't need them on there more than once. Is everybody okay with that?
And the 2 is just because there's a 2x to the 4th, right?
Right. So you have all the factors of 30 divided by all the factors of 2. So that's all the factors of 30 over 1. That's the first line I wrote. And then all those factors of 30 over 2. That's the second line I wrote. Yep. Good. So next we'll go and look at the graph. So let's see. I got to scroll over so I can see the problem there. I'll go back to the y equals, clear everything out, and then type in the polynomial exactly as I've written it. Oops. Nope. Squared minus 26x minus 30. Goodness gracious, I did it again. Whoa. Pop goes the weasel. Okay, so I got that typed in. Again, if I look at my list here of my RRT list, the smallest number is negative 30 and the biggest number is positive 30, so that'll be my x min and my x max. Then let's go ahead and hit graph. And so there's all of my action here happening right around there. So I'm going to go and say, like, well, that looks like maybe negative 6 or negative 7 out here. And that looks like just 1 or 2 over here. So maybe I'll do like, you know, like negative 8 to positive 3. Just so I'm only including the parts that I care about. I don't want a big long range, so it'll still be easy for me to count my tick marks. Okay. So let's look at what we got here. So that looks like negative 1, negative 2, negative 3, negative 4, negative 5. Negative 1 and negative looks like about halfway in between, so I'll say negative 1.5. And then that looks like halfway in between positive 1 and positive 2, so I'll call that positive 1.5. Now, do I know it's exactly 1.5 or negative 1.5? No, right? Like it could be something very close, like it could be negative 1.4. Or negative 1.49 or something. Like it's just, I can't tell just from looking at the picture. So when it comes to choosing one of these for my synthetic, to pick the one that looks like a whole number to me. So I'm going to start with the negative 5 straight away. Because those decimal ones, I don't know if that's like actually an irrational number or if it is the 1.5. If it is 1.5, notice that that is on our list. So it's possible that that is an actual value that we're interested in, and it's possible that it's some irrational thing that we wouldn't be able to find using the synthetic division. And there's really no good way to tell right from the jump if that's the case. So we'll go ahead. And here, if I look at that 4-term piece at the end, that is something that I notice can be factored by grouping. So I'm going to go ahead and do that mostly because when I look at those other values, I'm not so sure that any of those are going to work. It's very possible that those like 1.5 and negative 1.5 are like actually like, you know, like the square root of 2, which is like 1.4-ish. So it could be something irrational. But since I noticed that this piece is something I can use my factoring tree method on, I'm going to go ahead and do that rather than trying to do any synthetic divisions here. Do synthetic division with the decimal. You can do it, but it's just sometimes not very pleasant. So the first group I can take out an x squared. From the second group I can take out 2, leaving me with 2x plus 3. And there's a 2x plus 3 in both of those. And then that x plus 5 still comes all the way down. I notice the 2x plus 3 is linear, can't do anything more with that. And the x squared minus 2, well, that's 2 terms. Not a difference of squares because the 2 isn't a perfect square. And it's clearly not a sum or difference of cubes because the exponent is not divisible by 3. So this is a negative 1.5 we would have right here. But if we tried to do the positive 1.5 when we did the synthetic division, that wouldn't have worked, since the positive 1.5 is coming from the square root of 2 there. Just to kind of show you that, I'm going to go ahead and do that. It's not necessary that step that I'm doing right now. I'm just kind of showing you that the negative 1.5 would have worked. That right from the get-go that was going to be the case. And even if we had done it this way, so if we did the negative 1.5, we would have had this. And if I look at x squared minus 4, there's a greatest common factor of 2 in there that I can take out. Now, if I look at x plus 1.5, we hadn't, when we factored things, we didn't leave anything with a decimal in a factor like that, right? We've never done that before. We don't want to do that now. What we would do is if we, that gets rid of the decimal for me. Now, ideally, that the grouping wasn't the easier route to go there, but you could have still used the synthetic division in place. There's a little bit more to do to get there, but it was still okay to do that if you had tried to do that. That was asking me, or was it Rochelle? I couldn't tell.
Here's a shell.
Okay. Are you good with that? What we did there?
Yeah, thank you.
Of course. Okay. Should we move forward here today? So we have a couple more pieces that we can add in to our method that we've been developing here over the last couple lessons to help combat some tricky situations. So let's go ahead and do that, and then we'll do some examples to close out class today. The first is one I call the bend, bounce, straight theorem. And this, what the bend, bounce, straight theorem is going to tell us about is how many times a particular factor could be used. intercept, and that x-intercept, when we look at the graph, if there's a bend going on at that x-intercept, then we know that factor is used an odd number of times greater than 1. So it could be used like 3 times or 5 times or 7 times. That picture there is an example of what we mean by a bend. You see how the graph is like curving one way, and then it hits the x-axis and starts curving the other way? That's kind of what we mean by a bend. Is everybody okay with that idea? It's mostly just a visual definition. I mean, we could give it a technical one, but it's like not practical because all we're going to be using this for is looking at a picture. So the visual definition is going to be better for us than like some really technical like definition where we start having to talk about concavity and stuff, which is not helpful if we're just looking at pictures, which is all we're going to be using this to do. The next part, oops. We should say at the x equals a, then that factor is used an even number of times greater than or equal to 2. And I'm going to change this to say greater than or equal to 3, just so we're using greater than or equals in both cases. Greater than 1 and greater than or equal to 3 are basically the same thing if we're talking about integer values, right? What's the next whole odd number greater than 1? 3. So like greater than 1 is like 3, 5, 7. Greater than or equal to 1, or greater than or equal to 3 is still 3, 5, 7. I just figured it'd be easier if that matched. So the next one, what does a bounce look like? That's what we mean by a bounce. So you see how the graph kind of hits the x-axis and then goes back the same direction it was coming. Like it's hitting the ground and bouncing. Okay, so bounce indicates that that solution or that factor could be used an even number of times. So there's an example of what we mean by a straight. Everybody okay there? Okay, our next one is called the Irrational Conjugates Theorem. That says a picture though of like what those solutions are going to look like. Any of them might be going on. The next one is the complex conjugates theorem. Okay. So those are the new 3 pieces that we're going to be adding in today to our procedure. And we don't really have to do anything new for these. These are mostly going to be used when we look at our graph, and then to make decisions about what to do when we do our synthetic divisions. So let's just kind of do an example here without having to do the full method straight away. Let's say that we have a polynomial with the degree is 5. Its rational roots are plus or minus 1, 2, 3, and 6. And this is the graph that we look at. So let's think about what could be going on here. The degree of 5 means that I should be able to see 5 x-intercepts. How many x-intercepts can I see? Just 1, right? Everybody agree with that? According to the degree, I could see up to 5 of them. So what's going on here? Let's kind of make a little table to kind of sort through this. So let's look at what our possible solution sets could be. So each line in my table is going to represent a different kind of solution set. So the total number of solutions I have to work with is total, right? No matter which line in my table I'm going to be in, I'm always going to have to have 5 total solutions. Everybody agree with that? Okay. So I notice here that x equals -2. Is that a bend, a bounce, or a straight?
Bend.
That is a bend. That tells me that that solution could be used 3 times, 5 times. Could it be used 7 times? No, because how many solutions do I have in this problem? 5, so I can't go bigger than 5, right? But it has to be at least 3, and it has to be an odd number, so my choice would be 3 or 5. So I know that that could be 3, or it could be 5, right? Now, in the case that all 5 of them are here, that leaves no room for irrational solutions and no room for imaginary solutions. Everybody okay with that? I know there's no irrational solutions, though, in general, because if I look at the graph, I would still be able to see those x-intercepts. They just wouldn't necessarily correspond to anything on my RRT list. So I know there's no irrational solutions because I can't see any other x-intercepts, and you would still be able to see x-intercepts for irrational things. That leaves then, if I have just 3 times using -2, I must have two imaginary solutions in that situation. So when I do my synthetic division, I know I can be using -2 at least 3 times. Or I have to try something else, right? Does that make sense to you guys on kind of what I did there? Again, I haven't actually done any factoring. I haven't done any solving. What I've done is I've just kind of talked about how I can use this new pieces of information to give myself a better idea of like what to do with the synthetic division parts, right? I haven't really added anything new, any new steps. I've just kind of talked about what I can do with that. Is that okay? All right. You ready to try some examples here? Sound good to you guys? All right. Okay, so let's say we're asked to factor this polynomial completely. So right away I can tell that this should have 6 solutions, so at most 6 factors or at most 6 x-intercepts, right? Using the RRT, I just need the factors of 81 divided by the factors of 1. So the factors of 81 are just 1, 3, 9, 27, and 81. And then I'm going to go to my graph. And I'm going to get a picture of that. Okay. And we'll set our window here. So negative 81 to positive 81, that's going to be a big stinking window. I'm guessing we'll definitely be zooming in there. So I do this and kind of saw some stuff happen real close here, right? Everybody agree with that? So I can rule out that 81 was involved. Negative 27 is probably like almost a third of that distance. So clearly nothing going on there. 9 would be like a tenth of that distance. I still don't think anything's going on there. So I think I can probably safely say negative 3 to 3. And there I see some stuff. Now, notice this x-intercept at -3. Can you tell if that's a bend, bounce, or straight with what we have, what we're working with right there? I can't, right? Because it could be doing this, could be doing that. I need to see the other half of that x-intercept. So I am going to go back and extend my window a little bit further. I'll go maybe -5 so I can see a little bit past that to see what's going on. And I'm glad that I did, because it turned out that was important, right? So if you can't see the whole x-intercept, go ahead and change your window a little bit. Make sure you can see those. All right, let's write down what those x-intercepts are that we see and whether they're bend, bounces, or straights. So we have that one at -3. And is that a bend, bounce, or straight? Good. And then this one is in between -1 and -2, but it's closer to -2. So what do you think? Like -1.7 or something? Maybe 1.8? Something like that. Does it really matter what the decimal is? Why not? Grace, I saw you shake your head.
I don't know. I just know it doesn't matter.
Okay. Why it doesn't matter is because, is it going to be something on our RT list? No. So I can't use synthetic division on it anyways. So who cares what the decimal is, right? I can't do anything with that anyways. That's going to be a piece that I'm going to have to find later by factoring. I'm not going to be able to synthetic divide that away. But is that a bend, bounce, or straight? What do you guys think? That -1.7, that is a straight. I agree. And then we have this other one, this +1.7, also a straight, right? Now, right away, it appears that -3 is a rational value. But as we noticed before, since -1.7 and +1.7 aren't on my list up there, I can safely conclude that those are irrational. So I know that I can't use synthetic division to do these. So if we set up a little table here, so we have the solution -3. We have some irrational stuff. We know there's 2 of those. There could be some imaginary stuff. We can never see that, but sometimes we can conclude whether it's possible or not. And we have to total up to 6, right? So with the bounce, that solution could be used twice. Could it be used 4 times? Sure. Because 4 and then the 2 irrationals will give me 6, but that would force there to be 0 imaginary. Could it be used 6 times? No, because we already have 2 irrationals, and 6 and 2 is too many solutions then. So if we go back up here, if it was used twice, 2 and 2, I need 2 more to get to 6.
Why can't you use it 4 times?
Why can I?
Yeah.
So I have 4 here, 2 here, 0 there, gives me 6. Right, the bounces are an even number of times greater than or equal to 2. So it's still going to add up to 6 total if it's 4 there, right? Well, we don't. But because we don't know whether we have imaginaries or not, so we might, in which case we would only be able to use that solution twice, or we don't, in which case we know that we'd have to use that one 4 times. But we don't know. And there's no way to look at the graph and know. So what we do is we start with the assumption that we're going to be using it the minimum number of times, do our synthetic divisions, and then see where we're at. And go, okay, well, maybe I'm going to have to use this do 2 more divisions, or maybe I'm going to have something I can factor. We don't know yet until we do the synthetic divisions. Does that feel okay, though?
Yeah.
Okay. again, it's going to get easier as you get some more practice. This is the first example we're seeing. And the big takeaway is just remembering that you can use this one more than once, right? If you just keep doing that division until you get something you can factor, you should be in good shape. You know what I mean? Okay, so let's start our synthetic division now. So -3. I want to point out to you, when we looked at this polynomial, did anybody notice anything special about this polynomial? Yes, very good. So we have to make sure we put a 0 there in between the x to the fourths and the x to the seconds. That's very good. Nice job observing. It's easy to forget about that. Okay. So let's factor. Okay. So we know we can do the -3 synthetic division twice, at least, right? So let's do it again. I want to point out here, though, that this piece that you had could be something you could factor by grouping. But since I know I can do that, or do it again, let's just do it again and see if we get something even better, which I kind of like this even better because this is a 2-term polynomial, which is, I think, even a little easier to deal with. Everybody's okay there? Okay. So where we're at, we have x plus 3 that we did twice. And then we have the constant x, x squared, x to the third, x to the fourth, minus 9. Now that x squared minus, or x to the fourth minus 9, 2 terms. If we're going to try to factor that, first thing we check for is a difference of 2 squares. At this point, I'm hoping that you can recognize that pretty immediately as a difference of 2 squares. Do you guys agree? How would it factor using the difference of 2 squares? X squared minus 3 and x squared plus 3. Everybody's okay there? Leo?
Where do you get the x to the fourth?
So if I look at at the end of my synthetic division, I count from the right over, so the first number is the constant term, then my x coefficient, x squared coefficient, x third coefficient, and there's the x to the fourth coefficient.
Oh, so why is the x to the third squared?
Because I have 2 of them. It worked here and it worked there.
Okay.
You could write x plus 3 twice. That'd be fine too. It's just less writing to put the exponent on it rather than writing 2 of them. But you could write 2 of them. That's okay to do also. It means the same thing, right? Right? You could write it this way also.
Yeah, that's a good note.
Yeah, that's okay. No big deal. Whatever works for you. There's no preference on my part. I usually put the exponent on because it's just less numbers for me to write. But if it's confusing, just list them all. It's no big deal. Okay, so we're here. Can I factor x squared minus 3 anymore? No, because it's not a difference of 2 squares, because 3 isn't a perfect square, and it's certainly not a sum or difference of 2 cubes. Likewise, x squared plus 3, can I factor that anymore? Definitely not. It's a plus, so it's definitely not a difference of 2 squares, and it's definitely not a sum or difference of cubes, so we're done. So just pointing out here, this piece is the part giving us our irrationals, and that piece is the part giving us our imaginaries. So we were in that first line on our table where we had 2, 2, and 2. Okay? So again, there's, when we start the problem, there's some uncertainty, but we're able to say a whole lot more about the possible existence of imaginary things, right? and the possible existence of, or the likely existence of multiple solutions. We can certainly detect if something is being used more than once by looking at the graph. Now we can't tell you how many times more than once, whether in this case it was going to be used 2 times or 4 times. We didn't know that for sure, but we knew enough to get started, and the problem followed pretty nicely once we were able to do that. You know what I mean? So again, there's often not going to be a ton of certainty when you're doing these, but there should be certainty of at least well, I know I can at least do this much. I don't know if I'm going to be able to do more than that, but I know I could do at least this. Does that make sense? All right. How are we doing? We have, 25 more minutes? Let's do one more example. And that should be good, right? Okay. We have this bad-looking mama jamma here. But that's okay. Doesn't really change anything for us, even though it's a pretty long problem. We start the same way. So we have 7 solutions. The constant term is 4. The leading coefficient is 1. So my factors of 4 over my factors of 1 are just 1, 2, and 4. And then we go look at our graph and see what we can see there. So clear that out of there. Hi, Miss Anderson. What's new?
It's Friday.
That is a bonus,
Yes.
for sure. Who are we looking for?
I'm looking for the sprayer.
For the what?
The sprayer.
Oh, okay.
Is it Miss Williams' turn today?
I
believe it is.
Let's see, what's today? The 22nd?
Second.
Yep.
Okay. Thank you, sir.
You're welcome. Okay, so I typed in my whole thingy-majigger there. I'll set my window to -4 to +4, again, because those are the smallest and largest numbers for my RRT list. Actually, you know what? I'm going to do -5 to +5, because like I saw last time, if 4 is one of the values, I need a little bit past it to see whether it's a bend, bounce, or straight. So I'm just going to do one more or less than the biggest and smallest, just in case. That saves me from, especially in this case where the range is already going to be fine, I won't have to zoom any. Saves me from having to go back and zoom again if I do have something at 4, -4. So I'll hit graph and take a look and see what's going on here. Okay. So I see something at -1 and I see something at +2. Boy, that's, there's supposed to be 7 possible x-intercepts I can see. I definitely don't see 7 things, right? The good news is that both of those 2 things are on my RRT list. If I look at -1, is that a bend, bounce, or straight? Looks like a bend to me also, right? If you're not sure, you could zoom in closer to that spot and you should see it clearly looking like the bend. And then if we look at positive 2, is that a bend, bounce, or straight? That's a bounce. Okay. So let's go ahead and set up our table. So we know there's 7 total. The bend, the least number we could have is 3. The bounce, the least number we can have is 2. We know there's no irrational because we can't see any other x-intercepts, right? Everybody's okay with that? So 3 plus 2 is 5. I need 2 more to get to 7. Those 2 would have to be imaginary. Everybody agree with that? Now, I could also have 5, 2, and 0, or I could have 3, 4, and 0. Everybody agree with that? That those still are going to work out to give us 7 are still following the bend, bounce, straight rules? Leo?
Where do we get the first 3 from under x is -1?
So because it's a bend, I know it's going to be like 3, 5, yada. The bounce is 2, 4, 6, yada, yada, yada. So I know that those are the numbers that I can place under the -1 and the numbers I can place under the positive 2. But I know I really can't get to 7 because I need to put at least a 2 in the bounce column. You know what I'm saying there. So I just can pick things to get up to 7. And those are the 3 combinations, right? If I have less than 7, that's okay, because I can fill in with imaginaries what I'm short. But I can't have more than 7. So we're not sure which one of these 3 situations we're in. But like I've said before, we usually start with the minimum one. So we're going to try to do 3 divisions with -1, and then 2 divisions with positive 2. Or you could go in the other order. You could do positive 2 first and -1 second. But that's going to be basically my plan, because I know at least that much division I should be able to do. And then whatever's left, I should be able to tell if it's imaginary or if I can do a division with one of the other ones left. So that's my plan. Does that feel okay? All right. So I'm going to start with the -1s because I think that the arithmetic is going to be easier. Again, if you looked closely at the polynomial to start with, you should have noticed something. There was no x to the 4ths, so I have to make sure I account for that. -1 there. So that worked. Do it again. Notice here at the end, though, last 0 off. So I should be able to do -1 at least 3 times. So I'm going to do it all 3 times here to start. And now I'm going to switch to my positive 2s. I'm going to observe at this point that I would be able to factor that thing by grouping, but I know that doing another division with a 2, why not keep going? And now let's see what we got here. So I know I have x plus 1 to the 3rd because I have 1. That worked. And then I'm going to have x minus 2 to the 2nd because I see that 2 times. part constant x squared, so x squared plus 1. And if I try to factor x squared plus 1, can I do anything with that? Not a difference of 2 squares because it's addition. Not a sum or difference of 2 cubes because the exponent is 2, not a multiple of 3. So we're done. So we were still in that first line there. Is this feeling okay? Again, not much different than the process we've done before. You might have to do more synthetic divisions. But we know a little bit more about how many times we might have to use a specific number to do the synthetic divisions, right? The bend bounce straight helps a lot in that regard. Okay, we're going to stop here. I don't